Okay, this is the second video of chapter 7 about sampling distribution. By the way, I flipped my videos left and right because previously my right was on the left and the other way, so it was a little bit unnatural to me. Anyhow, and in the previous video, I said this chapter is about sampling distribution, random sample, which means that an experiment generates multiple outcomes at the same time, and we are interested in their average, right? So again, the simplest possible example is dice rolling. So we are going to think about two dice, right? You are going to throw two dice at the same time, so it gives you multiple outcomes, right? So x1 and x2 are the outcomes of the dice, and x bar is their average. Already it is a sampling distribution, even though it is super simple. Okay, so then let's think about the probability that the average equals 6. It's just, there is no trap, it's pretty simple. Just practice. Okay, now how do we think about that? Like there are 36 possible combinations, right? 6 possible outcomes from number 1, 6 possible outcomes from number 2. So there are 36 possible cases, and among them, only one will give you an average of 6 when both dice have 6. That is only one possible case. So the answer is 1 over 36. Okay, that's it. That's all. That's pretty simple, right? So for x bar, the average to be 6, you have to have 6 twice. That means the probability goes this way. So first dice has 6, second dice has 6, and they are independent. So you can use the special law of multiplication. So you can multiply them, and the answer is 36, 1 over 36. Okay, so basically this is how you calculate the probability distribution for x bar in this simple case. Like when when you are interested in x bar equals to 5.5, that means one dice has 5 and the other has 6. But it can be like 5, 6 or 6, 5, like we did in binomial distribution. So like you have to think about two different cases, and again use the multiplication rule to calculate single outcomes probability, like, right? So then in the end it becomes 2 over 36. Okay, so this is pretty basic, like calculus, simple computation. And then what I wanted to show you here is this is single dice distribution. When you have only one dice, you are going to get this distribution. 1, 2, 3, 4, 5, 6 have equal probability, about 0.16 something, like 1 over 6, right? So, but when you have two dice, range is pretty much the same from 1 to 6, but it's like more finely divided. And probability can be calculated like that. We just calculated probability of 6, probability of 5.5. Similarly, you may do the same thing for all the possible outcomes when you throw two dice, right? When you roll two dice, you can calculate the sampling distribution. Now I am going to increase the number of dice. Then of course it will be more difficult to calculate the probability, but you can still do it on computer, all right? I did that, and this is the distribution of when you have 5 dice. When you have 5 dice, the average of the 5 dice distributed like this. If you repeat the dice rolling infinite times, or of course it's calculated purely theoretically, right? You know, under the independence assumption, and increase it even more, 25 dice, right? Then it looks like this, like the cell is divided finely. And what's interesting is actually there is positive probability near 1 and 6. Still, it is possible that you have all 6 or all 1. That is possible, but of course, very, very unlikely, right? You have to have 1 25 times in a row. That is possible, but very unlikely. So probability is positive, but cannot be seen here, right? It's up to like the probability in the tail is really hard to see because that's that hard. That's unlike how unlikely those extreme values are when you repeat dice rolling 25 times. And what you can see here is now you see the idea. In the end, it looks like a bell curve. This is normal distribution, right? Pretty much like a normal distribution. But we started from a very uniform. It is not a bell curve at all. It's flat, perfectly flat. That is dice roll, right? But when you repeat, when you think about sampling distribution based on dice, it is a normal distribution, right? That is what I wanted to tell you. Like in the previous chapter, I said everything is normal distribution. This is why, right? This is the example, right? So starting distribution does not matter when you observe a sufficiently large number. Its average will be normal. That's why normal distribution is normal. Okay, so we are going to generalize this idea. There are more properties we can extract from this simple observation, simulation experiments. Like now, I am going to try different simulations with, like, of course, in reality, it is not possible. But see, in simulation, we can think about a dice with just a greater probability of 1. So 2, 3, 4, 5, 6 are equal, but 1 is twice more likely. Hard to imagine what dice, what it looks like, but in simulation it is possible. Then this is when you roll that dice once, then 1 is twice more likely. But when you repeat it 5 times, the average looks like this, right? Already, it looks like a normal distribution. But what you have to see here is the center is close to 3. When you use a fair dice, the mean is 3.5, right? It's perfectly symmetric here. But when you use a weird dice, then it is not exactly like symmetric. It's centered around. Center moves a little toward to the left. And when you repeat 25 times, it's already pretty much like a normal distribution. Again, the center is not exactly at 3.5. It's a little bit left of 3.5 because more probability of lower outcome, right? So this is another interesting simulation study. What happened if really any distribution converges to normal distribution? Okay, so I made a wrong, like weird dice. Still, it converges to normal. Another simulation. Now, I distort a dice so that 1, 2, 3 are twice more likely than 4, 5, 6. What would happen? You see, when you roll 5 dice, it's distributed like this. Again, the center is not exactly 3.5, a little smaller than that. And when you repeat 25 times, it's again a normal distribution, very much like a normal distribution. Okay, so I made a even weird dice. The probability is proportional to the outcome. 6 is 6 times more likely than 1, and like 3 is 3 times more likely than 1. So if you could make such a dice And if you repeat the experiment, what would be the distribution of average? So when you make 5 dice and roll them together, their average is distributed like that, like this. When you have 5 dice. And again, the center is greater than 4 because in this case, larger numbers are more likely. So the mean is greater. And like when you have 25 dice, the distribution is again another bell curve, very much like a bell curve, right? So what I wanted to show you through these simulation studies is that no matter what the starting distribution is, in the end, you are going to get a normal distribution, normal-like distribution, right? So even the repetition is pretty small. 25 is not a large number because whatever data you have, you are going to have more observations than 25, right? These days, you are living in a big data era. So if you increase the number from 25 to larger number, then it will be much smoother and much more like a normal distribution. Okay. Okay. So I told you 3 things like 3 studies, 3 different dice, imaginary dice, generates the same normal-like distribution. And I'm going to formulate patterns, extract common patterns based on these 3 simulation studies. First, the expectation does not change, right? So let's have a look. So when you have fair dice, the expectation is exactly 3.5. The center is 3.5. It does not change. Always the center is 3.5. Okay, so and now think about distorted case. In this case, the center should be a little lower than 3.5. It does not change. So even if you increase the sample size, even if you increase n, the center does not move. Like it's already always fixed here and here. Compare this one and that one, and again here. You see the center does not change. It's just, of course, the center depends on how you manipulated the probability, but that's maintained even if you change n. Right? That is pattern number 1. Pattern number 2, the variability decreases. Like extreme values are much more unlikely when you increase n, right? So let's go back. As I said, like here, 1 and 6 are equally likely as the other numbers, okay, in single distribution. But when you have 2 dice, already 1 and 6 are the least likely. That probability decreases relative to the center, right? That means more probability is concentrated near the center, right? The center has more probability than the tail as the number of dice increases. Like it is true to all the simulations. Like here, 1 is the most likely outcome at the beginning in a single distribution, but in the end, it's nearly unlikely, nearly impossible to have, right? Probability is nearly 0. Still pretty small. Of course, the other extreme is also unlikely. So, like that is the basic property of normal distribution. Probability goes down as you go down to tails. This is true to any simulation studies, right? So here again, like 6 is the most likely, but in the end, the average cannot be 6, right? So like very extremely unlikely to have an average of 6 when you repeat 25 dice, even if its probability is pretty high, like more than 25%. Okay, so that is pattern number 2. The variability decreases and like the tail probability decreases and more probability is concentrated near the center. That is like normal distributions property. And finally, the shape of the distribution is bell curve as n increases, right? So we will summarize our simulation studies conclusions into three patterns, right? The mean does not change, the variability decreases, and the shape is smooth bell curve. Okay, so I'm going to formulate them as properties. Like first property, the mean of the expected value of the sample average equals the expected value of a single outcome, right? So single dice expectation equals like with the expected value. You can calculate the expected value from a single dice. Whatever the probability is, if you know 6 probabilities, you can calculate its expectation, right? That is the same expectation for the average of multiple dice, right? Basically, you are repeating dice rolling, same dice. So sample average has the same expectation as a single average, right? A single outcome, right? Single outcome is not an average, okay? Then simple proof for two case, right? So you know the first dice and second dice have the same expectation because they follow the same probability distribution, right? Single dice, and then the average takes this form. The sample average takes this form, and if you take its expectation of the sample average goes like that, which is a linear form. So you may bring the addition and dividing by 2 out of the expectation. So it's like expectation 1, expectation 2 divided by 2. That is because they are the same. It is simply again just single expectation, right? No matter how many, you are going to get the same result. Okay. And second pattern was that the variability decreases, tail probability decreases. That can be represented by the variance or the standard deviation. And mathematically, you can show that the variance of sample average is single outcomes variance divided by sample size. So as sample size increases, denominator increases, so the overall variance will decrease. Okay, it's pretty interesting. So basically what we are doing here is we are connecting the sampling distribution, the distribution of multiple outcomes, the average of multiple outcomes, we are going to relate that to the distribution of single outcome. Mean are the same, but the variance is related, but it depends on the sample size. The idea is, remember, the variance includes a step that you square the deviations, right? Everything is squared inside the variance. So this divided by 2 is already squared, right? So we learned it in chapter 4, right? You may remember this. So you are adding 2 variances and divide by 2 square. So one of the 2 is canceled out, and in the end, 1 still remains. So denominator includes sample size. As you increase the sample size, the variance will inversely proportionally decreasing. Okay, that's pattern 2, right? And pattern 3, the distribution of x bar, the sample's average, converges to a normal distribution as the sample size increases. Okay, so it's pretty simple, like normal distribution. We already saw the histogram. So what's amazing of this is I'm not saying the original distribution has to be normal. No matter what the single distribution is, in the end, the average will be normal, right? As you saw from the simulations. So what you need is just like, and we already know the properties of normal distribution. And our conclusion from chapter 6 was that you only need two parameters to understand a normal distribution, mean and variance. If you know the mean and the variance, then you know everything about the normal distribution. That was normal property. And then how can we find the mean and variance? Using these two properties. The mean, so we only need mean and variance by property 3. Then we know the mean and variance from property 1 and 2. That means we know everything. This is how statistics works, right? So we put some names for this theory. First, law of large numbers. Law of large numbers, you may have heard about this name, but in statistics, theoretically, it means the expected value of the sample average is the same as the expected value of a single outcome for any n, no matter what the sample size is. But the variance of a sample average is the single outcome's variance divided by n, which means it converges to 0 as n goes to infinity. If the sample size is infinity in the limit, then the variance will be 0, which means the randomness, the variance of x bar will be 0, which means the randomness of x bar goes away, disappears in the limit, right? So it will be always true. X bar is not random in the limit, and it will converge to this point. Certainly x bar, certainly the expected value of x in the limit. Like it will be true. There is no uncertainty. There is no randomness if n is super large. Okay, that is the law of large numbers. Second theorem, center limit theorem, usually called CLT, for sufficiently large n, like in the limit f as n goes to infinity, the average sample average is approximately normal distribution, like converges to a normal distribution, right? And of course, the mean and the variance are given by these two results already, right? So it's an approximation, like and convergence in the limit. And so these two fundamental theorems are super powerful, as you can see, because they give you all the information you need, and they tell you the only distribution you need to know is the normal distribution. No matter what the starting point is, no matter what the single outcomes distribution is, you are going to get a normal distribution. So very powerful. And so we are going to use it repeatedly from now on. From the remaining 5 chapters, we are going to use those two like all the time. And the problem is, of course, the only problem is we need to have sufficiently large n. Then how large does it have to be? There is no scientific answer, but some like textbooks have a guidance like 30 or 35 as the minimum. Your data must be at minimum 35 or 30, but it depends on the situation. Like if your model is more complicated, you better have more sample size. But in general, so I would recommend like at least 100. And these days, sample size is usually not a big problem. Like those examples I showed you in earlier chapters had several thousands. Several thousand is not a big data anymore these days. So I don't worry too much about that. And the only problem is, like even if you have like 100 sample size, that's okay, but the normal approximation error will exist a little bit. Like it's always there will be approximation error, but just to be more accurate, you better have a larger sample size. So this is really fundamental theorem, super useful, powerful theorems. So we are going to study a little more how to use these theorems in the next video. Okay. Thank you for watching and see you in the next one. Bye.